Hello everyone, how you all doing? Good to see you here. Today I'm just gonna do some more maths. Okay, half of you are excited, half of you are really excited, half of you don't care. You're gonna click off this video, but just stick around because it's gonna be fun. Right, so let me just do this. Okay. Oh, I don't want to make myself too small, smaller than I already am. Okay, it's gonna take up this much space. Got it. Right, there's my iPad screen and I have my stylus and everything. Um, for today, we're going to be integrating the reciprocal of a general quadratic, okay? Then we're going to look at a specific case where you can actually factorize the quadratic using partial fractions, and then use that to find an identity, and then finally we'll take the limit of the identity. Okay, so first let's focus on the integral of this, okay? Integral 1 over ax squared plus bx plus c. That's just the general quadratic. That's the definition of a quadratic, right? Where a, b, and c can take any values. The only restriction to this would be that a shouldn't be 0, but maybe we could do something with that some other time. Okay. In fact, Michael Penn already has a video where he solves a quadratic where a is equal to 0 using the quadratic formula. You guys can check that out on his channel. So we're going to assume here that we can't factorize this quadratic, okay? Because, I mean, technically you can factorize every single quadratic, even things like this, like y equals x squared plus 1, right? This is a quadratic that you can't really factorize most of the generally, right? Because this equation, x squared plus 1 equals 0, has no real roots, right? X squared equals minus 1, so x equals plus or minus square root of minus 1, right? Which is actually plus or minus I, right? I is just square root of minus 1, that's the definition. However, you can factorize because the quadratic still has two roots. They're not real roots, but they're still roots. X plus I times x minus I. That's how you can factorize like any quadratic, right? Like even ones without real roots, right? But yeah, that's just out of the scope of this video. We're not going to go into the complex world today. I'm just trying to keep things real, you know? So instead, we're going to be completing the square of the denominator, which, if you're unsure what that is, if you have quadratic like this, you can rewrite it in this form, right? This is a completed the square form, where it's just a linear equation to the power of 2 times a factor plus another factor, right? I'll just put my cursor away. There we are. So essentially, how do we get there? First, we have to factorize out a like this, right? The reason we're going to do this is because we want this coefficient here to be 1 to make our life a little bit easier. Then I'm going to do something that looks a little bit goofy, a little bit unjustified, shall I say, and I'm going to justify that for you. So I'm going to add b over 2a squared and minus b over 2a squared, okay? It looks long-winded so far, but trust me, you know what, whenever someone says trust me, they're probably lying to you, but okay, so essentially the idea is take something like this, x plus or minus y squared. What is this equal to? Well, you can write it like this, right, as a product of two parentheses. And then once the dust has settled and once you've multiplied everything out like this, you eventually, I'm not going to do that for you today, but you eventually get x squared plus or minus 2xy plus y squared. Whoops, that's not a, I meant to do a superscript. Yeah. Why do I have a plus or minus here? Well, essentially, if you have x plus y squared, you will take the plus on the right hand side. If you have x minus y all squared, you'll take the minus on the right hand side. This is just to like generalize everything for you, okay? Now what then? How do we use this? Well, essentially, we want to write this in this kind of form, right? Of course, plus some other constant maybe just chilling around there, right? And essentially, we have, what do I call it? So this is what we said x squared would be. Let me just make it clearer for you. That is like x squared, right? This is 2xy. We just need a y squared somewhere, right? In order to find what y squared is, we need to find out what y is. We already know that the capital X and the lowercase x are just equal to each other. So if I write on the side here, 2xy equals b over ax, and we know that x, the capital and lowercase x's are just interchangeable with each other because of this over here, the coefficients match. We can cancel those out, and we get that y equals b over 2a. And so therefore, on the bottom line over here, that's our capital X squared, that's our 2xy, and that's our y squared, okay? Let me just rub all this out. And then in order to preserve the equality sign, we just need to minus y squared here, right? So x squared plus 2xy equals to x squared plus 2xy plus y squared minus y squared. And then you can take the x squared plus 2xy plus y squared and write it in the form x plus y squared, right? In our case, y is b over 2a. And then you're left with the negative y squared at the very end, plus c, okay? Then you get a times x plus b over 2a squared minus, we're just going to multiply this a with this to remove the b over 2a squared from the bracket. And you get b squared over 2a, okay, plus c, yes. Right, now to make things look nicer, you don't have to do this, but I'm just going to do it for you. I'm going to take this bit over here and multiply both of these. Let me see. I'm going to multiply the c term by 2a over 2a, right, to commonize the denominator of these two terms, and then I can add them up as a fraction, right? So I can write 2ac minus b squared over 2a, okay? I'm sure I'm allowed to do that anyway, right? And then I think we can take this quadratic and put it into what we had earlier. Give me a sec. Yes, I have realized that I've made a little mistake. Big mistake, not little mistake. I'm thankful that I spotted it earlier. But essentially, over here, the 2 and the a are both squared. So you should end up with a 4 instead of a 2, right? B squared over 4a. Therefore, I'm just going to replace this with 4a over 4a, and you should get 4ac minus b squared over 4a, right? Now that's what I'm going to replace into the integral, right? So the integral is equal to, what do we have inside the integral? 1 over what? A brackets x plus b over 2a squared plus 4ac minus b squared over 4a, okay, dx. It doesn't look nicer at all. It looks like we really messed up the form of the quadratic, but we have still preserved the equality, and that's all that matters in 2024, right? Apparently. Okay, what do we do now? What I'm going to do then is multiply the numerator and the denominator by 4a in order to, because I hate working with fractions within a fraction, right? A fraction within a fraction within a complex fraction, essentially. So I'm going to multiply the top and the bottom by 2a. So by 4a, sorry. This is going to be multiplied by 4a, and all this is also going to be multiplied by 4a. On the top, we clearly have a 4a. On the bottom, well, if we multiply this 4a by that a, we get 4a squared. Okay? And then we have x plus b over 2a squared. And this 4a and that 4a will cancel. That was the whole point of multiplying by 4a in the first place, right? So that we could remove the fraction within a fraction to just get a single fraction, right? And that's what we result in. Then I'm going to just, take the 4a and put it outside, because why not? On the numerator, by the way. And you're left with the integral of, I'm just going to put the dx on the top, 4a squared. I'm going to write it as 2a brackets squared, okay? And then we have the x plus b over 2a squared plus 4ac minus b squared, okay? That's what we have. Then I'm going to write this as equal to all this. All right, so the thing is, if we have this thing squared times this thing squared, we can just combine the brackets together to get us 2a times x plus b over 2a, all squared like this, right? Then we have the rest of the integrand, okay? So then what? We get 2ax plus b, right, squared plus 4ac minus b squared. Essentially what I did was I took this 2a and I just distributed it within the sub bracket, and you get 2ax plus 2ab over 2a. The 2a's cancelled with the b when they're next to the b, sorry. And that's what we get, okay? We get this 4a times the integral of dx over this weird, I don't even know what that is, right? And so the next step is to take a substitution. So I'm going to let u, I'm going to work in purple, I'm going to let u equal to 2ax plus b. I just want to make the integral look a little bit nicer, right? If you differentiate both sides, you get du over dx equals 2a. That's just the power rule, okay? And a is a constant, so it's just a multiple constant. So you differentiate the x, you get 1 times the 2a. So du over dx is 2a. The b will disappear when you differentiate because it's a constant with respect to x. So if du over dx is 2a, then du equals 2a dx, right? Another way to get that in just one step is just to implicitly differentiate. And so du over 2a is just equal to dx, right? And if we rewrite... Sorry, my brothers are just playing with each other. They enjoy that. Now anyway, we get equals 4a integral of, instead of dx, we had du over 2a, right? And the denominator is, well, there's 2ax plus b is just u, and we have that squared. Plus we have 4ac minus b squared just chilling on the outside, okay? This 2a factor over here, I can just bring it as a denominator at the front, divide the 4a by the 2a, and you're left with just 2, okay? So I'm going to write this as just 2, all right? Just for your pleasure, your viewing pleasure, okay? Now what? What do we do from here? I propose a idea where you split the function up into two possible cases, and I'll tell you. So the first case, case number 1, is when 4ac minus b squared is greater than 0. In other words, 4ac, what do we say? b squared minus 4ac is less than 0. Right? The second case is where we have 4ac minus b squared is less than 0, so b squared minus 4ac is greater than 0. Okay? Oh, and quick note, for the case where b squared minus 4ac is equal to 0, we just get the integral of 1 over u squared, which is negative 1 over u, right? So that's something that we don't have to worry about too much. Anyway, for the case number 1, and case number 2, for case number 1, b squared minus 4ac is less than 0, so the quadratic has no real roots, right? It either goes completely above the x-axis or completely below, right? No real roots whatsoever, only complex roots. Because this is what we call the discriminant of the quadratic, b squared minus 4ac. If you look at the quadratic formula for a second, let's say we have the quadratic equation, this, right? This means that x equals minus b plus or minus all this, right? For those of you guys who have left college or high school or whatever, trust me, I use this every day. Okay, so don't worry about that too much. But yeah, you know how we have a square root here, right? And in order to remain within the real world, we must have a number greater than or equal to 0 inside the square root. So we must have b squared minus 4ac greater than or equal to 0 in order to have one or two real roots, right? In our case, we have the discriminant less than 0. So the function, the quadratic just doesn't touch the x-axis at all, right? That's just something worth noting, I guess. And in the second case, we have b squared minus 4ac greater than 0. So the quadratic has two real roots. The quadratic touches the x-axis twice. If we have b squared minus 4ac equal to 0, then we just have a repeated root like this, where the graph just is a tangent to the x-axis. It only touches it at one point, right? It doesn't even go through it. It just does this, right? And leaves. Peace out, right? Okay. So let's work with the first case first, where 4ac minus b squared is greater than 0. So we have the integral of du over u squared plus... Okay, 4ac minus b squared, that's a positive number, right? For example, we have... I'll give you simple examples. So if you have an integral of 1 over, let's say, or du over u squared plus like 1 or something, right? You're just going to end up with inverse tan, all right? Whereas with the second case, if you have like u squared minus 1, you're going to end up with inverse hyperbolic tan, right? Plus c, of course. Let's work with the inverse regular tan first, then the hyperbolic tan comes after. So instead of writing 4ac minus b squared, I'm going to write the square root. I'm going to write 4ac minus b squared with the square root all squared like this, okay? The reason is so we could use a formula that I'm going to show you. So the formula is that the integral of dz over like z squared plus gamma squared, where gamma is a constant with respect to z anyway, can just be written as arctan or inverse tan. I'm going to use inverse tan instead. Tan to the negative 1, inverse tan of z over gamma times by 1 over gamma plus c, of course, which I'm going to ignore for now. Right? In our case, instead of z, we have u. Right? Instead of gamma, we have square root of 4ac minus b squared. Right? If you're unsure about the legitimacy of this formula, you could, I'm going to actually show you. You could take a substitution. Let z equal to, I don't know, like gamma tan of theta, right? So if you differentiate both sides, you get dz equals gamma d theta. And the integral just becomes, wait a minute, not gamma, gamma times the derivative of tan, which is secant squared d theta. Okay, I forgot that. And so if you replace the numerator dz with gamma secant squared d theta, and the denominator, well, z squared is just gamma tan theta squared, so gamma squared tan theta squared, plus gamma squared. You could factorize the gamma squared from the denominator out to get gamma squared times tan theta squared plus 1, right? And an identity you must know is that secant squared is equal to tan squared plus 1. So the secant squared and the tan squared plus 1 cancel, right? And the gamma cancels like this. You're just left with the integral of 1 over gamma d theta, which is 1 over gamma theta plus c, which I'm going to ignore, which is 1 over gamma times whatever theta was. So here, if z equals gamma tan theta, so z over gamma equals tan theta, then theta is tan inverse of z over gamma, right? So now, instead of having z and gamma, quite basic things to work with, we have u and the square root of 4ac minus b squared, right? And we just have a 2 chilling outside. So if we use the formula I just told you, we get 1 over gamma times tan inverse of z over gamma. In our case, that's what z is, and this is what gamma is, okay? Square root of 4ac minus b squared. So 2 times 1 over gamma, which is 2 times 1 over square root of 4ac minus b squared, times the tan inverse of z over gamma, or u over square root of 4ac minus b squared, right? Of course, you could rationalize the denominators of these by multiplying both the top and the bottoms by root 4ac minus b squared. I don't really think I need to do that at the moment, okay? Then, of course, we have plus our integration constant, which is c, right? Which I'm going to actually write at the very end. We don't really care about it. The next thing, or the final thing to do for case number 1, is to replace u with x. I said that u is equal to 2ax plus b from earlier. This means if you isolate x, do that, I'm going to do that in my head, you get x equals u minus b over 2a. Actually, I don't even need to, sorry. We already have u on its own. U is just 2ax plus b, okay? So I'm going to replace this by 2ax plus b. Tan inverse of 2ax plus b over the square root of 4ac minus b squared, right? Yeah, that's it, pretty much, okay? Of course, plus c, I don't really care about it that much. That's not the point of today's video. But yeah, that's the first case of the function, of the integral of the reciprocal of the quadratic. The second case, let's look at it now, where we have 4ac minus b squared less than 0. So reminder that we have this integral here, du over u squared plus 4ac minus b squared. When this is negative, or essentially, like, for example, du over u squared minus 1, we get hyperbolic stuff going on, right? So I'm going to take the integral and do the same thing that I did with case number 1, where you're at u squared plus... Okay, one thing first. I'm going to write minus b squared minus 4ac, okay? I haven't changed anything because if you distribute the minus, you get 4ac minus b squared. I'm just doing this such that you can write the integral in the form dz over z squared minus gamma squared, right? We're just a minus there. That's why I'm doing this. So you end up with u squared minus the square root of b squared minus 4ac, like this, squared, right? And what? We can derive, using the exact same approach with last time, that the integral of dz over z squared minus gamma squared is 1 over gamma times hyperbolic inverse tan of z over gamma, plus c, of course, right? And so you get 2 over the square root of b squared minus 4ac times arctanh, or hyperbolic inverse tan, of what, u over root b squared minus 4ac, right? Finally, replace the u with the x. U is equal to 2ax plus b, by the way, from earlier. 2ax plus b over root b squared minus 4ac, right? And so that's what we have, right? That's the two situations that we have here, okay? Firstly, with quadratics that have no real roots, and secondly, with quadratics that have 2 real roots, all right? With quadratics that have 1 real root, aka when b squared minus 4ac is 0, you're going to get this thing here is equal to 0, and you're going to get arctan of infinity, right? Which is pi over 2 or something. And you end up with like pi pi over 0, which is undefined, so you'd have to take limits. We can deal with limit things later, not regarding that specifically, but you'll see. Okay. So I'm just going to recopy everything. So from the start of the video, I said we had 3 things I wanted to discuss. The first thing was the integral of the inverse, the reciprocal of a quadratic, and we found out together that such an integral will equal 2 things. Either, what was it, 2 over square root of 4ac minus b squared times the inverse tangent of 2ax plus b, had to remember, over root 4ac minus b squared, plus some arbitrary integral constant, right? Or we get this instead, 2 over b squared minus 4ac, square root, times hyperbolic inverse tan of 2ax plus b over the square root of b squared minus 4ac, plus some random constant of integration, right? Where the first one applied for all b squared minus 4ac less than 0, and the second one, give me a sec. Yeah, my younger brother just into the room. He was asking for, where are you going? Why are you so dressed up? Yeah, don't worry about it. Okay. Oh. Okay. Yeah, now I'm ready. My software was glitching for a sec. The second case works for b squared minus 4ac greater than 0. Okay. So that's our function, all right? The integral of the reciprocal of a quadratic, okay? Now we can move on to the second thing that I wanted to discuss, the integral of a quadratic which you can factorize. We're going to use partial fractions first, then we're going to use the just general case to form an identity between, like, hyperbolic inverse tan and inverse tan and all that, and logs, you're going to see. So let's deal with observation number 2. Okay. So we have the integral of 1 over x plus alpha times x plus beta dx. Of course, once again, feel free to, on your own, mess around with complex values of alpha and beta. I'm just going to keep it real for now. Okay. This can be written as capital A over x plus alpha plus capital B over x plus beta, right? That's just the partial fractions integral technique. And if you cross multiply and you find a way to make these have a common denominator, you can eventually derive that a times x plus beta plus b times x plus alpha is going to be equal, like identity with 1 for all like x values, right? And so we just need to plug in convenient values of x for us that we can use to solve a and b, right? I'm going to choose firstly x equals negative alpha. If you let x equal negative alpha, you get a times beta minus alpha plus b times negative alpha plus alpha, which is b times 0, which is 0, right? So the b disappears. That's the whole point of letting x equal negative alpha, giving you a equals 1 over beta minus alpha, which can be written as negative 1 over alpha minus beta. And if we do the same thing where we let x equal to negative beta, we get a times beta minus beta, which is a times 0, which is 0. The a disappears, plus b times alpha minus beta equals 1, giving us that b is equal to 1 over alpha minus beta, right? So a is equal to negative 1 over alpha minus beta, and b is equal to positive 1 over alpha minus beta, right? we can factorize out the alpha minus beta like this, just outside the integral, and we're left with 1 over x plus beta minus 1 over x plus alpha, right, dx. And as you all know, integrating these two terms, you just get logarithms, right? You get natural log of x plus beta as the first one. Essentially, I'll tell you, the integral of f prime over f gives you natural log of f, right? Where f is a function of x. And the derivative of natural log of f gives you f prime over f, right? So yeah, here instead of f we have x plus beta, and f prime, derivative of x plus beta is 1, which is the numerator, right? Do the same thing with the other term and you get this, right? I'm going to ignore the plus c for now. You get natural log of, if you combine these two logs using logarithm properties, natural log of a minus natural log of b equals natural log of a over b, right? You get natural log of x plus beta over x plus alpha, right? And that is the general antiderivative, I guess, for the integral of 1 over x plus alpha x plus beta, right? With factorable quadratics. And given that the quadratic has 2 real roots, I'm going to have to assume that b squared minus 4ac is greater than 0, right? So we're going to have to take the hyperbolic tan definition for the integral of the reciprocal of a general quadratic, right? But yeah, anyway, that's the first way to get an answer. The second way to get an answer for the integral of... Did my pen just run out of battery? I think it did. Let me charge it real quick. Too many issues going on today. Okay, sorry for that. It's charged now. 6% at least. That's probably enough for a little bit of time. So, quick reminder that this is equal to... Oh, the pen is struggling to work. Oh, great, we're in for a ride today, aren't we? Okay, it works now, finally. Sorry about that. Reminder, this is equal to the integral of 1 over x plus alpha x plus beta, okay? Where alpha and beta are real numbers, of course. We're just dealing with reals for now. Another way is to take the integral and expand the denominator. What do we get? We get x squared plus alpha plus beta x plus alpha beta, right? And this can be written as the integral of 1 over ax squared plus bx plus c evaluated at the specific case where lowercase a equals to 1, lowercase b equals to alpha plus beta, and c equals to alpha beta, okay? So now we can use the formula that we had from earlier. I did want to use the normal inverse tan because it makes things easier, but I may have to take the hyperbolic definition instead, because once again we're assuming that the quadratic has 2 real roots. So what was it again? We get 2 over root b squared minus 4ac times hyperbolic tan inverse of 2ax plus b over root b squared minus 4ac. Okay? Of course, we're just going to do all this, right? We're going to replace a with 1, b with alpha and beta, alpha plus beta, and c with alpha beta, right? So if we act on these, square root of... Okay, wait. First of all, what is b squared minus 4ac? Well, b squared minus 4ac is equal to alpha plus beta squared minus 4 times a, which is 1, times c, which is alpha beta, right? And alpha plus beta squared, like this, is equal to alpha squared plus 2 alpha beta plus beta squared, right? and then we just have a negative 4 alpha beta chilling on the right. Okay? If we collect like terms, we get alpha squared minus 2 alpha beta plus beta squared, which, recall, is equal to this, right? Instead of having b squared minus 4ac, we have a square root around it. So if I just apply a square root around everything, square root, square root, square root, square root, you see the square root and the exponent cancel to just alpha minus beta. Okay? So we get 2 over root b squared minus 4ac is alpha minus beta times hyperbolic tan inverse of the denominator once again is alpha minus beta. The denominator 2ax is 2 times 1 times x, which is 2x, plus b, which is alpha and beta, right? So now we have derived that this thing, if I just highlight it, it looks like I like urinated on it, but ignore that for a sec, is equal to this thing. Why is it black? It's meant to be yellow, right? Cool. So yeah, therefore, we can safely conclude that the integral of 1 over x plus alpha times x plus beta dx equals 1 over alpha minus beta times natural logarithm of x plus beta over x plus alpha, which is also equal to 2 over alpha minus beta times the hyperbolic inverse tan of 2x plus alpha plus beta over alpha minus beta. Okay? The reason I'm ignoring the plus c's is because they're completely irrelevant and they cancel anyway, right? In our case. What now then? So now we've derived this interesting fact. We can probably take some sort of limit, okay? Now, the thing with this denominator of alpha minus beta here and here and here is, what if we had a case where alpha equals beta, right? For example, integral of 1 over x plus 2, right? Or the integral of 1 over x plus 0, God forbid, right? Which is just equal to integral of 1 over x squared, which is negative 1 over x, okay? But let us derive something like this using a limits, right? So let's see. We can say that the limit as beta approaches alpha of the integral of 1 over x plus alpha times x plus beta dx is simply equal to the limit as beta approaches alpha of, we're going to use the logarithm definition, 1 over alpha minus beta times natural log of x plus beta over x plus alpha, okay? Which is equal to, I'm just going to write it as a single fraction for sake of convenience, natural log of x plus beta over x plus alpha, right? Which I'm going to write as natural log of x plus beta minus natural log of x plus alpha, right? Okay, now what happens if are you allowed to just plug in beta equals alpha into here? Well, if you do that, you get, firstly, the denominator, alpha minus beta becomes alpha minus alpha, which is 0, right? The numerator becomes ln, or natural log of x plus alpha, minus natural log of x plus alpha, which is also 0. Because we have a 0 divided by 0 situation, we can use L'Hopital's rule, of course, right? Of course you saw that coming, right? Of course we're going to use L'Hopital's rule. How boring is this video? Don't say that, please. Please give me support. Differentiate the entire fraction, the top and the bottom, with respect to beta. Okay. Do this. Yes. Now, if you are to differentiate, first up, this natural log of x plus alpha over here, because that is not dependent on beta whatsoever. In the beta world, this is a constant, so we cross it off, it disappears, right? It's irrelevant, differentiates to 0. The same logic can be applied with the alpha on the denominator. So the alpha males have left the chat, right? We're just left with the limit as beta approaches alpha of the derivative with respect to beta of natural log of x plus beta over the derivative with respect to beta of negative beta, okay? Which is equal to the same limit of what? The denominator clearly differentiates to -1. The numerator, quick reminder that the derivative of a log is just equal to the derivative of the argument of the log divided by the argument itself, right? In our case, instead of having an f, we have x plus beta. The derivative of x plus beta with respect to beta is 1. And we have x plus beta, okay? So therefore we have negative limit as beta approaches alpha of 1 over x plus beta, which is simply equal to negative 1 over x plus alpha. We can just plug in beta equals alpha into there and we get the answer, right? And fun fact, if you started off with this integral and just let beta equal alpha like on its own, like this, right? 1 over x plus alpha squared, you would get negative 1 over x plus alpha directly. However, we just did it using the limit of a logarithm, right? Sorry. And therefore we can conclude, less obviously, that the limit of the hyperbolic inverse tan version is also negative 1 over x plus alpha, right? So we can write here that the limit of, as beta approaches alpha, of 2 hyperbolic inverse tan of 2x plus alpha plus beta over alpha minus beta all over alpha minus beta is simply, beautifully so, equal to negative 1 over x plus alpha. Right, how beautiful is that? Why don't we put in specific values and see what happens? For example, the limit as, let me think. Let's take the integral. Let's see. Okay, let's take the integral of 1 over x squared plus 5x plus 6 dx. This is easily factorable. It's just equal to x plus 2, right, times x plus 3. How do I know this? Well, essentially, in order to factorize this is recalling back to GCSEs to like a long time ago, where you find two numbers that multiply to make 6 and add to make 5, right? In our case, we have 2 and 3. If you add 2 and 3, you do get 5, and if you multiply them, you indeed do get 6, right? And if you were to expand, you get x squared plus 3x plus 2x, which is plus 5x, plus 2 times 3, which is plus 6, which matches with what we have, right? And essentially, we get that dx, which if we use our integral definition from earlier, what did we have? We essentially should expect to get 1 over alpha minus beta times log of x plus beta over x plus alpha. So we can rewrite this as 1 over x plus alpha times x plus beta dx. My phone, man. Evaluated when alpha is 2 and beta is 3, or vice versa, doesn't really matter because commutativity. Which gives us, from earlier, 1 over alpha minus beta times logarithm of x plus beta over x plus alpha. Of course, evaluated when alpha is 2 and beta is 3. So you get 1 over 2 minus 3 times log of x plus 3 over x plus 2, which is equal to log of x plus 2 over x plus 3, right? All I did there was rewrite this thing as -1, because that's what it is, and put the -1 as an exponent inside the logarithm, which in turn flips the fraction around, right? Or reciprocates, essentially. So that's what we get if we use the definition of what's it called? If we use the log definition, what if we use the hyperbolic inverse tan definition? We get that this is equal to what is it? Yes, this stuff over here. Where is it? 2 over alpha minus beta times hyperbolic inverse tan of 2x plus alpha plus beta over alpha minus beta. Let me just put that in for you. 2 over alpha minus beta times the hyperbolic inverse tan of 2x plus alpha plus beta over alpha minus beta. Right? Of course, evaluated when alpha and beta are 2 and 3. Right? Giving us 2 over 2 minus 3 times hyperbolic inverse tan, that's a h, that's not a, of 2x plus 2 plus 3, which is 5, over 2 minus 3, which is negative 1, right? Giving us negative hyperbolic inverse tan of negative 2x plus 5. We can probably cancel the negatives out, giving us 2x plus 5 here, right? Arctanh of 2x plus 5, essentially. So therefore, natural log of x plus 2 over x plus 3 is equal to arctanh, or hyperbolic inverse tan, of 2x plus 5. That's a lovely identity, I guess, that we have concluded, right? This is only a specific case, so it's not really interesting to me. It might be to you, but yeah. And quick reminder once again that if you take the limit as alpha and beta approach each other, or as one approaches the other, it's the same as integrating just 1 over x plus alpha squared, which gives you negative 1 over x plus alpha, which you can also get by using the logarithm definition over here and applying the limit and L'Hopital's rule, giving you negative, the exact same answer, which can conclude us, which we can conclude that the limit of the arctanh definition also gives us negative 1 over x plus alpha, right? To me, that's just beautiful. I don't know about you guys. Maybe you feel an air of apathy around you. I feel an air of subscriptions, likes, and not money yet, because I haven't reached 1,000 subscribers yet. Please subscribe if you haven't. Please subscribe. Without begging you too much. You don't lose anything. And I'm incentivized to make more of these rants, essentially. Whether it's insulting mathematicians or something, or I'm just kidding. I've never done that before. I will never do that. But yeah, that's where we can, I guess, safely conclude the video, right? Quick recap once again. We took the integral of the inverse of, the reciprocal of a quadratic. Using completing the square, we assumed that we can't factorize. We cleaned up the integral, took a substitution, split the integral into 2 cases, where you have one resulting in an inverse tan, and another resulting in an inverse hyperbolic tan. Okay? And we wrote over here just a general integral, absolute monster of a thing. If you want to take a screenshot or whatever, it's too small for your screen, but you know. The next thing we did was look at a general case, a specific case, where we assume you can factorize. And of course, we assume alpha and beta are real. However, I could imagine this being possible for complex values as well. Okay? That's what I think anyway. Yeah? So, that's what we did. We did the partial fractions. We found the unknown values of capital A and capital B to be negative 1 over alpha minus beta and the positive version of that. And took the logs and we got this as the answer, right? Log of x plus beta over x plus alpha divided by alpha minus beta, right? If we do the same thing using the hyperbolic arctan definition, we get this here highlighted in yellow. The reason we use the hyperbolic once again is because the hyperbolic one works for quadratics with 2 real roots, and we're assuming alpha and beta are real, so we're assuming that we do have 2 real roots, right? However, if you don't assume that, then of course feel free to use the inverse tan definition instead. I've tried out the limiting process with that, and it works with that 100% as well. Okay. Anyway, next what we did was we took the limit as alpha approaches beta, which essentially gives us the reciprocal of a quadratic where the quadratic is a perfect square, right? We took the limit of the log and the stuff, and we used L'Hopital's rule, and we got a lovely answer at the end, which equates to what we would have gotten with the easiest method. That helped us safely conclude that the limit of as beta approaches alpha of the arctanh definition gives us the same thing, right? Just a safe thing to assume. So yeah, thanks for watching, everyone. If you have any suggestions for me, please in the comments spam me with, don't spam me, just kindly, gentlemanly, like give me something to reply to, please. If you spotted any mistakes in the video, if you spotted any improvements, maybe you want me to do a dark background next time, I might do that. Or you just have a suggestion, anything you want, please send whatever you want, okay? But with all that, thank you so much for watching. Have a good day.